let's go one step further and sort of see if we can clean that up a bit more and basically look at exactly what it would look like, right? So by the way, this unit that I have drawn over here, what operation is it doing? This is a MAC, right? So the MAC that you probably have heard a lot about already and you will hear a lot more of in this course, the multiply accumulate, this is exactly it. Alright, now the way that I could do this would be, I take two memory blocks, right, and over here I start storing the values x of n minus 1, x of n minus 2, and over here I store the values a, b, c corresponding to the data locations 0, 1, 2, 0, 1, 2 respectively. Okay, so I can just use one external counter over here and feed this as the address to each of these memory blocks. Okay, and along with that I will have this multiplexer out here that basically needs to check for whether counter is equal to 0. Okay, that's used in order to decide whether I have the feedback 0 coming in or something else happening over there. Okay, now look at my architecture, it's starting to look more and more general, right? My values, the x of n values are now stored in a separate memory block. My coefficients are stored in a separate memory block. If I want to change the coefficients, I just have to change the values in some memory, right? And that memory is being read out one element at a time. So it's a regular SRAM type of block that I'm talking about over here. Okay, what is the address going to that block? It's essentially something that is just a counter. By changing the limit of the counter, instead of going up to 0, 1, 2, if I change it to 3 or 4 or 5, I can change the number of taps in the filter, right? And in fact, I can probably actually say that, the sequence of steps to be followed is something like this. Initialize by setting counter equal to 0, and I'll take some variable, I'll call it next, and set it equal to 2, right? And then go into a while loop that says whenever the counter is equal to 0, what I need to do is reset the accumulator, update the value in the memory mem1 of next with something that's coming from the input, right? So this is basically the x of n storage, and next is equal to basically next minus 1 modulo n, right, where n equal to 3 here. Okay, what does that next minus 1 modulo n do? We'll see that in a moment. Essentially, why am I doing this? I'm sort of trying to be a bit clever over here in terms of how I do the shift register. Okay, we'll just look at that in a moment. After this, the next step would essentially be, after all of that thing has been done, multiply and add mem1 of counter with mem2 of counter, and do counter equals counter plus 1 modulo n. Okay, so what's happening out here? This set of steps out here is essentially trying to do, it's trying to check once in every 3 clock cycles, that is whenever the counter becomes equal to 0, there is some bookkeeping that needs to be done. What is the bookkeeping? Reset the accumulator to 0, load the new input into some location in memory, and that location in memory that I am going to load it into, change that for the next time around. Okay, so if you look at how this works, the counter I am going to assume is basically, or rather the counter, the way that I have written it over here is counter will go 0, 1, 2, 0, 1, 2, because modulo n, right, percentage n basically means when it reaches 3, 3 percentage 3 will become 0. It's a modulo counter. Okay, this is essentially something called a circular buffer. Okay, so what we are doing over here is, in hardware it's very easy to implement a shift register. The moment we start thinking about memory blocks and software, shift registers are no longer very efficient, because shift registers involve moving a large amount of data around, right? Every piece of data needs to move into an adjacent location. Even from the point of view of hardware, that's actually a bad idea, for the simple reason that it's probably going to end up consuming a lot of energy, right? Why is that? Because toggling of inputs, right? Let's say that I have a 100 tap filter, there are 100 elements that need to get shifted, right? Whole bunch of bits toggling, whereas what I really need to do is keep 99 of them the same, throw out the oldest one and replace it with the newest one. That's what I'm doing here. Okay, I store one new variable called next, initialize it to 2, and every time the counter becomes 0, that is once in every 3 clock cycles, I take whatever I've got as input and store it into mem of next, and decrement next, so that next time it becomes 1. Okay. Actually no, my mistake, I should have done that the other way around. It should be plus 1. You know, I think I need to make 2 minor modifications here. This should be plus 1, and it could actually be initialized to 0 itself. Okay, so what will happen is, the first time around x of 0 that's coming in will go into location number 0 in mem1. Okay, the next time after that x of 1 will go into location number 1, then it will go into x of 2 will go into location number 2, etc., right? And so we will have a circular buffer being built up over there. When the next value comes, it will overwrite the oldest one, it will overwrite x of 0, and I'll get next time it will overwrite x of 1, then overwrite x of 2, etc. Okay, so always by doing this kind of a circular increment, I am guaranteeing that the oldest value that was stored in that buffer is the one that's going to get overwritten. Okay, now what was the point of this exercise? Why did I write out this something that looks like software? The basic idea is to show you that the level at which I have written this software is literally controlling each and every register and every hardware element. Okay, this is what is sometimes called RTL code, register transfer level, right? I am working at the level of registers and literally telling you at every clock cycle, at every step, how are those registers getting updated. Okay, that level of detail, if I can provide, it's register transfer level code, which is very easy for a hardware compiler to convert into actual hardware. How will it convert it into hardware? Over here it's very clearly defined, right? Counter is a register, next is a register, accumulator is a register, mem1, mem2 are memory blocks. A while loop is, well, doesn't even require any implementation in hardware. How does a if condition get implemented in hardware? It's a multiplexer. Okay, so if select is equal to 0, something happens. If select is equal to 1, something else happens. Okay, that's precisely what a multiplexer does. Okay, so each and every step that I have written over here is something that's easy to implement in terms of hardware. Okay, so we now already have the basics of what a generic architecture for solving something like the FIR filter problem could look like. Okay, where do we go from here? Any questions? So what we can do with something like this is, if I want to generalize the idea, what I'll say is, what was it that I actually had over here? I had something that this was compute, this was memory, and this along with the wires etc. that it involved is what? Control. Okay. So in other words, I can think of any architecture or any problem that I want to solve in terms of something that I will call a data path which has the ability to do computations, and a controller, right, where the controller, in addition to just sending out, having counters and so on, can send any kind of signals. It will be load signals, it will be start signals, it will look for ready or done signals from the data path and then decide what to do next. All the complexity, the decision making is hidden away inside the controller, and the data path just does simple arithmetic. Okay. Usually this is then combined along with a few other things. In particular, there is something called a register file, but you could also have memory blocks, right, and the output of the data path could be routed to any of those depending on what the control says. Right, the control could also determine how the register file is activated so that you can write values into it. The outputs of this in turn could come through some kind of a large multiplexer, and go into the data path. Okay. Once I have got to this level, depending on what I put into the controller, for all practical purposes, I have got a programmable system. Okay. My data path has to be able to respond. I give it 2 inputs, or 1 input or 2 inputs or 3 inputs, whatever, and I give it the corresponding control signals. It does something, chugs away a little bit and gives me an output. Okay. The controller can then take care of deciding what those inputs are. Where are they coming from? Are they coming from registers? Are they coming from memory? Are they coming from the outside world? Right? Where are they going? Are they going back to registers? Are they going back to memory? Are they going to a D to A converter? Are they going to a display? Anything of that sort. Okay. So the controller essentially separates out what is happening with how it is done. Okay. In general, when we are talking about hardware architectures, these are important concepts to keep in mind, because all the hardware designs that we will be looking at, we will primarily be using a tool called high level synthesis for the rest of our design process, right? All of it will involve this kind of structure. There will be some elements of the code that you write which will get inferred as the data path, the computational elements, and the rest of it is basically a question of figuring out the control logic around it, okay, and providing the right signals to the controller. Okay. All right, we'll stop here for today.